this set of notes, we're going to look at implicit functions and differentiation. It corresponds with section 4.6 of the textbook. Now you will find that this chapter is fairly short. I want you to have at least seen this material before and been exposed to it, but we are only going to do a handful of examples. So far up to this point, we've only considered functions of the form y equals f of x, which defines y explicitly as a function of x. And so this function assigns to every real number x in the domain exactly one real number. And the graphs of these functions is a set of all points x, y such that y is equal to f of x. And we usually visualize the graph as a function, as a curve for which the vertical line crosses the curve at most one time. And so here I've got a couple examples from previous note sets of functions that we've looked at. And we can see that if we were to draw a vertical line anywhere on any of these graphs, that vertical line would only pass through the function one time. And again, we could draw a vertical line anywhere on any of these graphs, and that would be true. So there's no place on these graphs, if we draw a vertical line, we're going to cross over the curve more than once. But there are other curves that we could draw on the xy plane that do not pass this vertical test. And it's also possible to define y implicitly as a function of x. So for example, consider the equation of a circle with radius r. And so here I have a circle with radius 5, but we can obviously see if I draw a vertical line, it's going to cross through the circle twice. So we would say that this is an implicit function of y. Now it is possible that we could rearrange this to write this as a function of y. And your textbook actually does this, but your textbook leaves off this plus or minus, and that plus or minus is important. So I want you to note that in your book, it's going to claim that you can do that without the plus or minus, but you really can't. And the reason for that is if you just have the plus, what you're going to draw with the plus sign is the top part of the circle, and with the negative sign out front, you draw the bottom part of the circle. So we really do need the plus or minus in order to draw the full circle. And so what we could do is we could consider the plus side separately and the negative side separately and use the chain rule to take the derivative, and we could get the derivative that way. But we have to be very careful, because remember, when we talk about a derivative is really the slope of the tangent line at a particular point. So for example, if we were to consider when x is equal to 2, so I'm going to draw that vertical line back here. Here is when x is equal to 2. And we see that we cross the circle twice. Now up here, for any of these, when we talked about at a single point, and we only crossed the curve one time, we would just have a single point that we had to worry about the derivative at. Well here, there's actually two places on this curve where x is equal to 2. And so for that reason, when x is equal to 2, there's actually two potential tangent lines. We could have a tangent line here, or we could have a tangent line here. And so when we talk about evaluating the derivative, it's no longer good enough to just know what x is. We actually have to know which of these y values we're at. And so what you're going to find is when we actually find the derivative of y, or y prime for these implicit functions, is y prime, or that derivative, is going to have y in its formula. And the reason for that is, again, we need to know which of these 2 points or which of these y values we're at. Whereas when we took the derivative up here, for any of the previous ones, we've never had y in the derivative. So in other words, we'd have y prime equal to something, and on the right hand of this equation we would never see a y. And the reason for that is we didn't need that information, because we only crossed x once. When we drew that vertical line at the x, we only crossed the function one time. And so again, for that reason, now when we take the derivative, we're going to see that it's going to have a y in it, because we have to know at which of those points we are. Alright, so we're going to look at a couple different examples. Now, these examples are going to use all of the tools from the previous section. They can be a little tedious, so I do want to warn you, just take your time. We're going to do them piece by piece. But we aren't really going to need any new skills to do these, but we are again going to need all of those rules that we've had previously. And so to take these implicit differentiation, what we do is we set up our equation, and then we're going to differentiate both sides of that equation, and then we're going to solve for the derivative. And so we're going to look at a couple examples of how we can do this. So the first one we want to find is the derivative of y with respect to x of 1 over 2xy minus y to the third equal to 4. So the first step we're going to do is we're going to take the derivative of both sides with respect to x. So how I'm going to write this is I'm going to have d dx, and then the function I'm taking the derivative of. And so we've seen notation like this before. Now we know that anytime we take the derivative with respect to x of a constant, that's just going to be 0. So the right hand side of this equation is equal to 0. Now it's possible that on the right hand side that won't be equal to 0, and you'll actually see an example in the homework like that. Now here on the left hand side, we could use that summation rule, and this is going to be equal to the derivative with respect to x of 1 over 2xy minus the derivative with respect to x of y to the third. Okay. Now, to make this a little bit easier for myself, I'm going to probably want to not have this fraction, so you're going to see I'm going to change that here in just a second. Now what I want to do is I've got two different derivatives here. So I've got the first one, make that a little thicker. I've got the first one and I've got the second one. So what I'm going to do is I'm going to find these two derivatives separately and then put them back, put the whole thing together. So first, we're going to find the derivative with respect to x of 1 over 2xy. Now, to make this a little bit easier on myself, I see that I do have a quotient here. I've got 1 over 2xy, so I could either use the quotient rule, or I prefer to use the power rule. So if I want to use the power rule, I could rewrite this as 1/2 d dx of x to the minus 1, y to the minus 1. So I can see that the power rule is going to apply, but also I've got x times y here. And this is a really important fact here, is remember that y is a function of x. So y is not a constant, so i.e. not a constant. If y were a constant, we could just pull it out of the derivative. But here, in examples like this, y is actually a function of x. And so you can think of it as being like an f of x. And so since that is a function of x, we have to make sure that really we end up applying the chain rule when we go to take this derivative. All right. So first thing we're going to do here is I've got a function of x, which is x to the minus 1 times a different function of x. So in other words, I've got a product of two functions of x. So by the product rule, this is going to be equal to 1/2. So I'm just bringing that 1/2 out, and now I'm going to take the derivative of this whole thing here. Well, if I'm going to apply the product rule, remember we could call x to the negative 1 the u and y to the negative 1 the v, both being functions of x. And so here I could have x to the minus 1, and then I need to take the derivative of the second function. So that is going to be the derivative with respect to x of y to the minus 1 plus the derivative, oops, that should be an x there, not a y. Fix that. Plus the derivative with respect of x to the negative 1 times y to the minus 1. And so that's application of the product rule. Now, in order to take this derivative, because y to the minus 1 is a function of x, or y itself is a function of x, so I have a function of x to the negative 1 power, this actually requires the chain rule. So now, by the chain rule, I have the 1/2 comes forward, the x to the minus 1 stays, but now I have to take the derivative of this. And so remember from that previous section, we had that generalized power rule. So using the generalized power rule here, I'm going to have minus 1 times y to the minus 2, but y is a function of x. So I also have to include or multiply by the derivative of y with respect to x. And so notice up to this point, anywhere that I have written the derivative notation, I had the derivative with respect to x of this function here, derivative with respect to x of this function. And so now I'm going to change that to be the derivative with respect to y dx, because I'm just taking the derivative with respect to this y right here. So don't get lost in that, that quick change we're not changing the notation. I really am using a different notation here. All right. And I realized when I erased that highlighting a minute ago that I accidentally deleted that piece. So I'm just going to add that back in. All right, and so now I need to finish out what I've got here. So I had the 1/2 down, the x to the minus 1 came down. I took the derivative of y to the minus 1, where y is a function of x, so we got this whole piece. And then here, now notice this derivative, the next piece, that derivative just went with x to the minus 1. So really, I probably should have put parentheses around these. So then I've got plus. Now the derivative of negative 1 to the x, there's no chain rule needed here. That is just straight using the power rule. And then the y to the minus 1, that just comes down because we weren't, at that point, we had already applied the product rule, and so that was just that function. All right, so now we need to go through and we need to simplify this sum. So here, this is going to be equal to 1/2. Here I'm going to have negative x to the minus 1, y to the minus 2 times the derivative of y with respect to x. And so notice that is its own term by itself. That's what eventually we're going to solve for. Minus x to the minus 2, y to the minus 1. All right, so that was just this first derivative that we needed to find. So next, we need to find the derivative with respect to x of y cubed. And so again, similar to before, we need to use the chain rule here. So by the chain rule, we've got the derivative with respect to x of y cubed is equal to 3 times y squared, but y is a function of x, so we need to multiply by the derivative of y with respect to x. And so just constantly keep in mind here that y is not a constant, it's a function of x. So that's really where this implicit differentiation, that's where it's different than what you've seen before. All right. Okay, so now again, going back up to what we were trying to do, remember that we're trying to find this whole piece here. So we found the first term and the second term, so now we can place those together. So we now have looking at the first term here, we have 1/2. And notice that both of these terms have a negative, so I'm actually just going to make that negative 1/2, x to the minus 1, y to the minus 2, the derivative of y with respect to x, plus x to the minus 2, y to the minus 1. And then our second term, we took minus the derivative with respect to x of y to the third, and we found that that was equal to 3y squared times the derivative of y with respect to x, and we set that equal to 0. So now to finally get to the actual derivative, our second step with our implicit differentiation is we're going to solve for dy dx. So the very first thing I'm going to do is I'm going to multiply through by my negative 1/2 so I can separate those terms out. So I have negative 1/2 x to the minus 1, y to the minus 2, dy dx minus 1/2 x to the minus 2, y to the minus 1 minus 3y squared dy dx is equal to 0. Next, I'm going to move this second term. I'm going to add it to both sides of the equation and move it over to the right. So I have negative 1/2 x to the minus 1, y to the minus 2, dy dx minus 3y squared dy dx is equal to 1/2 x to the minus 2, y to the minus 1. I'm going to pull the dy dx term out, because again, that is an actual term. We're saying that's the derivative of y with respect to x, multiplied by negative 1/2 x to the minus 1, y to the negative 2, minus 3y squared. And again, that is equal to 1/2 x to the minus 2, y to the negative 1. And then finally, here we can solve for dy dx, which is what we're looking for. And so in the numerator, I have 1/2 x to the minus 2, y to the minus 1, divided by 1/2 x to the minus 1, y to the minus 2, minus 3y squared. So here is our derivative. I am going to manipulate this to simplify this term some, because typically we don't want to have fractions inside of fractions, and we don't want to have negative exponents inside of a fraction in the numerator or in the denominator, so we kind of need to change things around. So the first thing I'm going to do is I'm going to multiply everything through by 2 divided by 2. So notice that's really just multiplying by 1. But that 1/2 is going to cancel in the numerator, so I'm going to x to the minus 2, y to the minus 1, divided by x to the minus 1, y to the minus 2, minus 6y squared. And then again, I don't really want to have these negative exponents up here. So next what I'm going to do is multiply both the numerator and the denominator by, right down here, multiply by, and here we're going to multiply by x squared times y divided by x squared times y. And so if we do this, in the numerator we're going to end up with just 1. Now x squared times y times x to the minus 1 times y to the minus 2, that is going to leave me with an x times y to the minus 1, and then we're going to have minus 6 times x squared y cubed. And then last, I want to get rid of this y to the minus 1, so I'm going to multiply by y over y, and if I do that, I'm going to end up with y in the numerator, and in the denominator I'm going to have x minus 6x squared y to the 4th. And just to make sure that I did not drop a negative sign. So it looks like I did up here. I dropped a negative sign right here. So I'm just going to go through and add that negative sign in. There we go. And so that is our derivative. And so notice that our derivative has a y in it. And this is again because if we think of what these graphs look like, so if I go up here, here's what the actual graph of this function looks like. Notice there are places that if I were to draw a vertical line, I'm going to cross the function twice. And so it's not good enough just to know where x is, I also have to know where y is in order to actually find that derivative, because the slope of the tangent line is going to depend on which place in that function we are. So this example, this one was pretty complicated, but you do see you've got to apply the chain rule, the product rule. We had to apply lots of different rules that we saw from the previous, and we really need to keep track of, is y a constant or is y a function of x? And so for all of these, y is a function of x. So let's do one more example. This one is a little bit easier. This one's going to be very similar to what you're going to do for your homework. So here we have the formula for an ellipse, and you can see this is what this ellipse looks like. So obviously if we draw that vertical line, we're going to cross the function twice. So we'll start here with our step 1. And this is where we're going to take the derivative of both sides of the function. So notice on the right hand side we have the derivative with respect to x of a constant, so that's just going to be 0. And then we know that if we're going to take the derivative of sums, that's equal to the sum of the derivatives. Okay. So now looking at each of these, the first term that we have is the derivative with respect of 2x squared. Well, we don't need to do anything special here. We can just apply our power rule. So we're going to have 2 times 2 is 4 times x to the 2 minus 1, which is just 1. Next, for our second term, keeping in mind that y is a function of x. So for the second term, we are going to have to apply the chain rule. So we first use our extended power rule. And so our extended power rule says that we're going to have 4 times y to the 2 minus 1, which is just 1. But then I also have to multiply by the derivative of y with respect to x. And so again, applying that chain rule. And then for our third term here, notice that we have the derivative of x times y, both of which are functions of x. So for this one, we're going to have to apply our product rule. So here we're going to have 3 times, and then my two different functions of x are x itself and y. So you could think of this as u being equal to x, v being equal to y. The derivative of u is just equal to 1, and the derivative of v is dy dx. So now writing out my product rule, I'm going to have x times the derivative of y with respect to x plus 1 times y. And again, this is equal to 0. So now we're going to want to go through and collect like terms and simplify. So here I've got 4x plus, now notice I've got two terms that have the dy, and then I've got one term over here that does not. So let's collect our dy terms. So I'm going to have dy dx times 4y minus 3x, and then that minus 3 is multiplied by the y is equal to 0. So again, I got dy dx times 4y minus 3x is equal to 3y minus 4x. And then now step 2 is to solve for dy dx. So dy dx is equal to 3y minus 4x divided by 4y minus 3x. And here we have that derivative. And so again, notice the derivative not only depends on x, but it depends on y. And the reason for that is, if we're going to find the slope of a tangent line to one of these points, we have to know where we are in terms of y as well. Because, for example, when x is equal to 0, there are two different tangent lines. And so we need to know which one of it is that we're going to be looking at, and so that's why y is part of that derivative. So again, the purpose of this chapter, and this one is a little bit harder than the other ones. I just want to make you aware of implicit differentiation so that you have seen it before. It's another tool that you have. We won't work with it a whole bunch, and so you'll notice in the homework here I'm only asking for 3 problems because, again, I just want to make sure that you are exposed to this idea, not that we're going to be working with it a whole bunch. And so, as always, if you have any questions, please let me know.